this lesson is just touching upon the quadratic formula. You've probably seen this before, but what it does is allows us to find a relationship between the roots of a quadratic equation and its coefficients, which are a, b, and c. But I'm just going to use 3 examples, and I'm going to talk about how they're relevant to the quadratics we'll be looking at. Okay, so we have coefficients a, b, c, and again a, b, c, and a, b, and c. So when we substitute these in, we get 4 plus minus square root of 4 squared minus 4 times 2 times 1, and then this becomes plus 4, and then 4 squared is 16, minus 8 is 8, all over, I've missed a bit here, so 2 times 2, which is 4, so there you have 4 over there as well. And for this one, you get, well, this becomes plus 4 squared minus 4 times 1, all over 8. So this comes plus 4. And then in here, 4 squared minus 4 times 4 even, apologies, 4 times 1. It's going to be 0, okay? So what's going to happen in here is it's going to be just a 0, and the square root of 0 is obviously just 0. All over 8, and for the last one, again you have minus 1, and then you have 1 minus 1 squared minus 4 times 5 times 2, so that becomes 1 minus 4 times 5 is 20 times 2 is 40 minus 39. Okay, all over, and 5 times 2 is 10. 2a and 10. Okay, so look, exploring these roots here. So what are we going to get here? If we type this into a calculator, you get 0.1129, and here, for your second root, you get 1.7. Then over here, well, what was going to happen? Well, 4 over 8 plus or minus nothing. We're just going to get the same root twice. So you have equal roots. You have a half here. So they're both the same. Then what about over here? Well, we have 1 plus minus the square root of negative 39. Well, you can't actually take the square root of a negative number. So what you'd say here is there are no roots. You know, this it can't be factorized. Okay, so there are no roots. Okay, so how is this relevant to what we want to know about? Well, basically, you can think about it in this way, okay? Whereas before, I think this was 1.29, and this was 1.7. If you think about this as a quadratic, okay, so this is 2x squared, 4x, etc. So this would have the shape something like this, okay? We're saying it's cutting the x-axis at 0.29 and 1.7, okay? What about this one here? We're saying it's got a double root, so that means it's just gonna touch. It's just gonna touch the x-axis here at x equals 1 over 2. So what we call like a double root. Okay. What about this one here? We're saying there's no roots. So what would that look like visually? Well, you can just think of it as it's just a parabola that never touches the x-axis. There's no interaction between the two of them, so there can be no roots. So that leads us on to thinking about the discriminant. Okay, so the discriminant is part, well, you can see here, it's part of the quadratic formula. It's this b squared minus 4ac aspect of it. You see that the thing that's different in the 3 of these is that the value of the discriminant. Okay, and that kind of produces 2 values. This produces 1 value twice, and this one produces no values. So what's the relationship here? Well, we can use the discriminant to determine the nature of the quadratic roots, okay? So when, as before, like when we had the square root of 8, so when the discriminant is greater than 0, what we're going to get is roots that are real and unequal. So these roots are real in the sense that they exist, they actually exist, and they're not the same root, so they're unequal. You have the scenario where b squared minus 4ac is equal to 0, and then the roots are real and equal. So they are real, so they do exist, but they both just have the same value. Okay, so that was the roots x equals a half scenario. And this last scenario here is when you have b squared is less than b squared minus 4c is less than 0. So when you have the roots are non-real. So when you're saying the roots are non-real in the sense that they don't exist in the traditional way of thinking about them, beyond the way that's beyond the scope of the course, looking at complex numbers.